Hi everyone and welcome to today's video on set notation and sets of numbers, part of the Methods 1 and 2 course over here in Australia. Now hold on, stop. If you're about to hit that stop button, don't. Let's keep going. This stuff's awesome. Maths is universal and I can guarantee you what I'm about to teach you is in your course somewhere. So it's really good to see you and just keep watching. Now, if you are new to my channel, I'm Darren, otherwise known as MaffsGuru. And it's my job to sort of try and help you get better at maths, basically. I'm a small person, trying to do a pretty large job here. So if you can do me the honor, over there in the corner is a button that says, or an arrow that is clicking to a button that'll let you subscribe to my YouTube channel. I really appreciate it if you could, and actually you get a couple of your mates to do so as well. Would make me feel like I'm doing this for a reason. Now at any point through this video, leave a comment below, ask me questions, let me know what you're thinking, let me know how good the video is. But okay, enough of this now, you want to get on, don't you? Set notations and sets of numbers. Now as is normal as I grow smaller, up there you'll see an arrow that points to what we're going to learn today. And the interesting thing with all of this stuff is basically it's all language. If you can invest an hour or two, and trust me, this video is not an hour long, but if you can invest an hour or two learning, almost rote learning these particular terms, then I can guarantee you all the rest of the work we do in methods will be so much easier. Okay, and I promise you the next video is almost as important as this one because it's the foundation of how we describe functions throughout the whole course. So we are going to start with a recap, and actually, as I say here, there isn't really much to recap. Everything we do builds on what we've done before, but this is a whole new language. We're now going to change inequalities into a new notation that uses brackets, and we're going to use Venn diagrams, and we're going to use intersections and all sorts of stuff. But, you know, I actually like to think of maths as being complicated by a guy called Barry over here in Australia. And he wants you to learn certain words. So for example, the first word that I want you to know is the word set, which is nothing more than a collection of objects. Now we normally give sets a capital letter. Let's try that again. Actually make it look tidy. We actually give sets a capital letter. We have an equals, and then we do things like 1, 2, 3, 4, 5, 6, and 7. So this may be a 7-sided dice and all of those individual outcomes. Now, believe it or not, you've already met this when you did Venn diagrams, and I talked about that just a moment ago. Venn diagrams are freaky, awesome. You may be sitting there going, nah, don't understand those at all. It's okay, it doesn't matter, no big deal. But the idea of being able to have numbers grouped together and standing for something is what this is effectively about. I could also say that B in this situation might be the numbers 2, 3, and 4. Now, obviously you can see that B actually is the same as some of the numbers in A, and that comes as well with the word contains. What is an element? Well, basically, in this situation, the number 2 is an element of B. Yes, thank you very much. But as is usual with Barry, he wants to try and confuse us and use a little Greek letter or a letter. And there we go. We have a particular letter that stands for in. Now, you're going to say to me, what do you mean by that? Well, for example, if I had this, the X is in B. Now again, notice the way I've said that. X is in B. Now what do I mean by B? Well, I suppose, as I've just said here, the numbers in B, 2, 3, 4. And this notation actually comes very important because later on in the next video, when I start talking about domains and ranges, I may say to you things like X is in something like that. Now, while you're not going to understand that now, and if you do, that's awesome, later on, that's how we express absolutely everything in maths, right? With this here is called interval notation, this here stands for my domain, and that there is obviously the word in. So again, add that to your vocabulary. Then a subset. Now, I just talked about that a moment ago. We know that B was actually contained within A, wasn't it? Those numbers, if we go back and just remind ourselves, the numbers 2, 3, and 4 appeared in A. And so we can actually describe that using mathematical notation. And we say that B is contained within A. Now, I didn't trick there. It is a C with a line underneath it. That means contained within. Now, you can't have just part of B contained within. Every single number that is in B must appear in A for us to be able to write that. So the question is, what if all of B isn't contained in A? Well, lo and behold, we actually just put a line through it, all right? We put that line through it to show that it's not contained within. Right, I talked about Venn diagrams, and again, just remember, this is all about the language. Here's an example of a Venn diagram. So here is event A, and here is event B. Now, although in general terms we talk about it as probability, as events and stuff, actually here it can mean all of those sets as well. So we've got 1, 2, 3, 4, 5, 6, and 7. Actually, I've just called this B. I did that slightly earlier. Let's call it C. And the numbers 9, 10, and 11. Now, at this moment in time, what do you notice? Well, if you've remembered your work from last year for year 10, you'll know that these are called mutually exclusive. Exclusive. Okay, a mutually exclusive means that there is no overlap. Now, in maths, overlap is really, really important to us, and we call it a strange name, intersection. Well, actually, it's not that strange, really, because if you think about roads, roads have intersections. And what is an intersection? It's where they cross. It's where they meet or where they are the same. And the same thing actually happens with Venn diagrams. So when two diagrams overlap, this section here, where they join or they overlap, that's called our intersection. So let's put some numbers into this. We could have the numbers 1, 2, 3, 4, 5, 6, 7, and 8, and that was a 5. Now in this situation here, let's call that D and E. We know that D and E share one common number, and so that overlap, that intersection, is called, or be the number 5. How would we write that? We would say that D is intersected with E. And if I wanted to express that in terms of numbers, I'd say equals the squiggly bracket and the 5. Now you're actually judging my squiggly brackets at the moment, aren't you? Which is sad because I can't draw them properly. Yes, hopefully you do better than me. So intersection is this N, this N. Now again, you've met it before. A lot of times we use the word and. I'm going to ask you from now to dispense with that, throw it away. It's complete gibberish. And in fact, it will mislead you with some of our answers. What about this word union? Well, again, taking it back to my Venn diagram. Union is where we actually include all the numbers inside. So if I was going to look at D union E, all right, so that actually now looks like it's due, lol. I'd write the numbers 1, 2, 3, 4, 5, 6, 7, and 8. And I would make sure that I've put commas in front of all of those numbers or between those numbers. Now, I like Venn diagrams. Why do I like Venn diagrams? Well, A, I'm a maths teacher. B, because they make my life easier. Sadly, lots of people make mistakes. If I had actually written down there that element D, that set D was the numbers 1, 2, 3, 4, and 5. Don't forget the commas, MaffsGuru. Oh. And I wrote down that E was equal to 5, 6, 7, and 8. When it's written in this form, it's a huge trick, because when people now say, well, what is DUE? What they tend to do is go 1, 2, 3, 4, 5, 5, 6, 7, 8. See what I did there? I doubled up on that 5. I forgot that they were overlapped and I made a silly mistake. So we need to be very, very careful there. The last one that's important in terms of terminology is what we call the set difference. And basically it excludes. So in this situation here, if I had A with this slash B or a backslash B, it means the elements that are in A and not in B, all right? So the elements in A and not in B. Now, realistically speaking, the word here, not, is really, really important. Why? We'll come to that in just a moment. Right, Barry wanted to think of numbers having some sort of group. And we can group numbers in all sorts of different ways. We can have double odds and evens and, primes and composites and all sorts of different names. We've got 4 other ways of classifying numbers. And obviously, as I say here, we all want to belong to a group, don't we? I'd quite like to be, I don't know, popular. Oh my God, that's so sad. And interestingly, a song from Wicked. Too much information. If you want to be popular, don't forget, subscribe in the corner. I know, shameless plug, just trying it out. But we can actually categorize numbers in lots of different ways. Now, firstly, the most important one, and the one we use all the time, is this real numbers. Now, you have to draw the letter R very much like that. Do you see what I did? The 2 lines and then the R. You're going to reuse real numbers pretty much everywhere in methods. Now, real numbers are, as I say here, everything that goes from negative infinity to positive infinity. See what I've done there? So one way we could describe this is say there is negative infinity I want to go that x is less than or greater than, sorry, it's greater than or equal to minus infinity, but less than and greater to infinity. Cool, that's a tongue twister as well. That's one way of doing it, using inequalities. Real numbers are literally everything. They're decimals, they're whole numbers, they're fractions, they're surds, they're just every single number in the world is a real number. But then we actually narrow it down and say, well, okay, I want to think about rational numbers now. Now, rational numbers, again, you've met. How have we met rational numbers? Well, because rational and irrational. Rational numbers are any numbers that can be expressed as a fraction. So for example, 2/3 or 4/5 or I don't know, 9/100ths. They're all obviously fractions. They're rational numbers. But then funnily enough, so is the number 7, -3, 6, 12. They're all rational numbers because once again, I can turn them into fractions by dividing by 1. And you're probably going to say, well, aren't all numbers rational then? No, because pi cannot be written in terms of a single fraction. Okay, so pi is irrational. So effectively, we're probably taking out, from our real numbers to get to our rational numbers, we're taking out all the odd ones, the ones that just don't quite fit in. We don't know what to do with, really. Then we go down to integers. Now, if you are a computer programmer, you will know what an integer is because you'll be using them all the time. But integers are basically just whole numbers that can be positive or negative. So examples are -6, -5, -4, -3, -2, 1, 0, 1, 2, 3, 4. And we can continue once again to infinity and beyond. Okay, Buzz Lightyear, love, love, love. Integers are whole numbers that can be positive or negative. And then to make life just that little bit more interesting, and every now and again, we can see things here called natural numbers. That is an n with a double line between it. Now, natural numbers are effectively positive integers. Really, really important, yes? So in this situation, you'd be looking at 1, 2, 3, 4, 5, 6, and onwards to infinity. Now, have you noticed the one number I've missed? And that seems to be the number 0. And I hate to tell you this, ladies and gentlemen, but 0 is neither positive or negative. It is neither of those. And so because it says quite clearly here that natural numbers are positive integers, 0 doesn't get included, which actually causes a bit of an issue, but I'm going to show you how we solve it in a moment. Now, we can write intervals. We can write solution sets in lots of different ways. And one of them I did just a moment ago, but here's a different one. X is greater than 3. Now what that means is our X value can take 3.1, 3.01, 3.001, all the way up to infinity. And if I was to draw this on a number line, for example, if this was the number 1, 2, 3, I would put a circle on there and an arrow and literally point it off to infinity. I wouldn't color the circle in because it's not equal to. We can have something like, I don't know, X is less than or equal to -4. Now this time I've made it less than or equal to. How do we do this then? Well, here is -4, -5, -6. So color this one in because it's including and point it. Now, do you notice which way my inequality is pointing? My inequality is pointing that way, so does my arrow. One above it, which way was my inequality pointing? That way, and so that's the way my arrow goes. So there's two ways of using inequalities, and I suppose we could have something like -4 is less than or equal to X, which is less than 10. And what does that particular inequality mean? Well, again, probably preaching to the converted, and I'm sure you know this, but now X can take all of the values between -4 up to, but not including 10. Again, there is no equal sign underneath that inequality, so it cannot include 10. Now, I don't know about you, inequalities confuses everybody, and as far as I'm concerned, people go, no, don't like it, don't want to do it, don't want to do it. And so we come up with something called interval notation. This is really, really important. We are going to use this throughout the rest of the course. And so the thing to notice is we are going to use square brackets to include a number. We are going to use curved brackets to mean up to, but not including that number. And you can say, what on earth are you talking about? Well, let's go back. Let's say that X is greater than 3. When I drew that number line, I started at 3 and I went all the way to infinity and beyond. So imagine I could write this as 3, infinity. Here is my smallest value, and here is my highest value or largest value. Now, obviously, we've got to find a way of saying including and not including. And as it turns out, if we have a square bracket, it means, sorry, try that one again because that's not going to fit my example. A square bracket means including. Did this x value include the 3? No, because it doesn't have the little equal sign. And so we do a curved bracket to stand for not including. And believe it or not, infinity has a curved bracket as well. I'll come back to that one in just a moment. So that here is interval notation. Now, today I was asked a question that said, well, hold on a moment, that looks suspiciously like a coordinate. And yes, it does. Barry, once again, thanks, mate. He's looking for ways to confuse you. Now, how do you tell the difference between a coordinate and an interval? Read the question. The question will tell you. It is very, very clear, I promise you, when one's a coordinate and when one's an interval. So let's have another example. X is less than or equal to 10, for example. Now, if I was to do that on a number line, my highest number would now be 10. My lowest number would be minus infinity. So we would have minus infinity to 10. Does it include the 10? Yes, because I have that sign there. So including the 10 is a square bracket, but infinity is always a curved bracket. And you're going to go, but why is that, Maths Guru? And I'm going to say to you, sadly, infinity is a construct. It's an idea. We don't know what it is. We certainly can't write down a physical size of infinity. It's just something that sort of makes our life better. It's actually nice to know that in space, it goes on to infinity and beyond. You see how ludicrous that is? It doesn't even make any sense. You can't go beyond infinity because it's just an idea. Anyway, so every time you see an infinity sign, you write a curved bracket. So going back to my real numbers, what were my real numbers? Everything from minus infinity to plus infinity, yes? So my real numbers now can be re-expressed as minus infinity to infinity. Curvy brackets, comma in between them. This is my smallest value. That is my largest value. And now you have everything you need to know about, yes, interval notation. Now again, Barry tries to make things complicated. I'm going to scroll in, or zoom in a little bit on this one here. And there are 4 other ways of describing intervals and sets of numbers. Now, the first thing to notice here is the curvy brackets. Yes, those curvy brackets mean we're dealing with a set of numbers. So how do we decode this? Well, firstly, there's my curvy bracket, x colon. All it says is you're going to deal with numbers that have some relationship to x. There might be a formula coming up, there might be some sort of inequality coming up, and lo and behold, yes, there is, x is greater than or equal to 0. So what this is the same as saying is I'm now going to have the numbers 0 and onwards to infinity. And I can't do that because actually this doesn't tell me whether I'm dealing with natural numbers or integers or rational numbers or real numbers. So if it doesn't tell me, we actually assume it's all real numbers, which basically means any number greater than 0 can go in that bracket, or greater than including 0. What about this one here? Well, this one here is saying x has got to be, that's my value, that's my thing I'm looking at, is falling between 0 and 1. Well, in which case, that would be the same as 0 and all numbers up to, but not including 1. So actually, writing this is really hard because, you know, if it's not including 0, I can't put 0 inside that bracket, but hopefully you're getting the right idea. Here, what does this mean? It looks more complicated. It says my x values are going to be greater than 0 and in that situation can only be in my, that's it, rational set, all right? So Q, rational set. See what we're doing there? So now it can only be numbers that are bigger than 0 and not pi or whatever else. This one here starts with a formula. Basically that means the way we're going to create my set of numbers is by multiplying n by 2, and it's saying let the values of n be 0, 1, 2, 3, and so on. So this one's really easy to do because what I'm effectively going to end up with is my 2 times table, and so it goes on. Right, so this notation is designed to trick you. You have to learn what it means. Now finally, the last part of this video, and I'm sorry it's 20 minutes long, but so important, is this. We use these all the time in methods, like all the time. And for example, you will get used to, not the next video, but the video after, things like this. Sorry, that's supposed to be a comma, silly mistake. F of x is equal to x squared minus 2. Put that comma in there. All right, that there is function notation. And what do you notice? You notice here is my interval and here is my letter R. Now, it's not always interval notation here written in that sense. We can use other letters, and these are 5 ways of being able to do it. So first things first, rubbing this out, what do you think this means? Well, we've got the double R, and we've got a plus on top of it. So all that means is positive real numbers. It just wants positive real numbers. What about this one then? Hopefully R with a minus, negative real numbers. What about this one? Now, that should really be R plus and a U and a 0. Yep, okay, the U for some reason hasn't printed on this screen. Real positive numbers and 0? No, or 0. It can't be and 0. You can't have a positive real number and 0. They can't both exist. It's either real numbers or 0. This one here is all real numbers but not 0, and that's a definite slash there. Where would we have an instance of real numbers but not 0? Why would we want to exclude 0 as one of my possible numbers? Coming up in the next video. And finally, this one here is basically, interval notation saying that, well, okay, our values fall between -3 and 0 or 3 and infinity, yeah? So in this situation, we are looking for values that fall between -3 and 0 or 3 and infinity. Ladies and gentlemen, this is so cool. I'm so glad you made it to the end of the video. If you've made it to the end of the video, leave a message below if you did. Thank you very much. But otherwise, it's pretty much over. We were dealing with set notation and sets of numbers. Go out there, learn this stuff. Learn the notation, learn the real, learn the natural numbers, learn all of this stuff. Life will be so much easier for you. Okay, now if you haven't over there is a doohickey that will ask you to subscribe. Please click on it and ask 2 of your friends to do the same, and I promise you I will be deeply grateful. Below it is a video loading, which will be very much along the same lines of the ones you've just been watching. And I think that's it for me today. So thank you very much for watching. Just about to record the second most exciting video. I look forward to seeing you again. Take care. Bye-bye.